Hello and welcome back. In the last lecture, we used the probability axioms to prove some equalities, and now we would like to use them to prove a few inequalities. And maybe along the way, we'll see an interesting question. So again, we're going to use the three axioms. We're going to prove some inequalities, including the union bound, and then we'll get to a problem that whose reward is not $64,000, but actually $1.4 million. Okay, so let's start. So remember the three axioms. There were the non-negativities. The probability of any event is at least 0. Unitarity, probability of the whole sample space is 1. And additional, if you have two disjoint set, the probability of the union is the sum of the probabilities. Okay, and in the last lecture, we used them to prove a couple of equalities, and now we want to use them to prove some inequalities, except that we want to start with 0, and that could be viewed as equality. It is equality, but after that we'll move to inequalities. Okay, so let's start with, as I said, with essentially 0. What is the probability of the non-event? So remember that unitarity says that the probability of the whole sample space is 1. But what about the probability of the empty set? Did we just forget to mention it? No. We're going to show that the probability of the empty set can be proved to be 0. Okay, so the proof is going to be simple. So remember that the whole sample space omega is the union of can be written as the union of the empty space and the whole sample space, and therefore the probability of the omega, the whole sample space, is the probability of the empty set union with omega. This union is disjoint, and therefore this probability by the additional is the sum of the two probabilities, probability of the empty set plus probability of omega. Probability of omega cancels on both sides, and what we get that the probability of the empty set is 0. Okay, so that was pretty easy. Again, it's a one Lego result, and it says that the null event has nil probability, where nil is 0. Okay, cool. So next, we want to start talking about a couple of inequalities. So we once said that the probability of any event is between 0 and 1. So the left side, the probability of any event is at least 0. We know from an axiom. That's just the non-negativity axiom. It says the probability of A is at least 0. And so the only thing we need to show is the right side. The probability of any event is less than or equal to 1. These, by the way, are called universal bounds, that for any event A, the probability is at least 0 and at most 1. Right. So so what we want to show is the right side. The probability of A is less than or equal to 1. Okay, we start as usual. A union A complement is omega, and therefore the probability of A union A complement is the probability of omega. And now we observe that A and A complement are disjoint. Oh, sorry, going the other way first. So the probability of omega by unitarity is 1. Okay, and then we observe that A and A complement are disjoint, and so the probability of the union by the addition rule is the sum of the two probabilities, probability of A plus the probability of A complement. And then we use the non-negativity rule to set that the probability of A complement, this is an event, so its probability is bigger than or equal to 0, and therefore this is going to be bigger than or equal than just P of A, right? Because we take here P of A and we add something which is non-negative, so we get a result which is at least as large. Okay, and what do we get? We get the probability of A is less than or equal to 1. Okay, so we get the probability of A is less than or equal to 1, right? So it says the probability is always between 0 and 1, and as I said, some people call it universal bounds. Okay, now this is actually a fairly important result. The probability of A is less than or equal to 1, and it's particularly important if you come to UCSD. I have a colleague here, he teaches probability, and he's pretty lenient. If he asks you about probability of an event and you don't quite get it right, maybe its probability is 0.01 and you said its probability of it's 0.99, you can still get an A+ from him. But if you said the probability is bigger than 1, any event, he asks you the probability of any event, you said probability is bigger than 1, like 1.01, he says you get an automatic F. So if you come to UCSD, just keep that in mind. All right. The next inequality we want to prove is about probability of subsets. So if A is a subset of B, then very naturally we expect the probability of A to be less than or equal to probability of B. And here's the proof, simple proof. A is a subset of B. Then here's the picture. Here's A, here's B. We know that the probability of A should be less than or equal to probability of B. We just want to prove it. And we can write B as A union B minus A. So B as A union B minus A. And therefore the probability of B is the probability of this union. This union is the disjoint union. And therefore it's going to be the sum of these two probabilities, the probability of A plus the probability of B minus A, but the probability of B minus A is bigger than or equal to 0, and so by the non-negativity, this is going to be bigger than or equal to the probability of A. So we got that the probability of B is bigger than or equal to the probability of A as we wanted, right? So that's what we want to show. Probability of B is bigger than or equal to probability of A. Now, at this point, things start getting a little boring, I think, just using those axioms, those Legos. Again, and here we use 2 of them. So you might say, oh, this is so obvious, like, why are we even bothering doing that? And so the only thing I say is we shall see. And the last inequality that we'll discuss is actually a pair of inequalities that have to do with unions of sets. So if you have 2 sets A and B, and you ask what can you say about the probability of the union, so here are the 2 sets A and B, and we're asking what we can say about the union probability. So we'll have a lower bound and an upper bound. The lower bound will say that the probability of A union B is at least the maximum of the probability of A and the probability of B. Very natural here. The probability of the union is at least the probability of A, and the probability of B is at least the maximum of them. And the upper bound, also natural, says that the probability of A union B is at most the probability of A plus the probability of B. Again, very natural, because we have here probability of A plus the probability of B. It should be at least the probability of the union. Okay, so first let's prove the left side. So we know that A is a subset of A union B, and B is a subset of A union B. So both A and B are subsets of A union B. Okay, and therefore by the subset result that we just proved, we see that the probability of A and the probability of B are both less than or equal to the probability of A union B. And if you have 2 numbers that are less than or equal to what's written on the right side, then the maximum is also less than or equal to this right-hand side. Okay, so we get that the maximum of both of them is also less than or equal to probability of A union B. Now, how about the right side, the upper bound? So, well, this we can use the principle of inclusion-exclusion. Here is our pi. It will tell us that the probability of A union B is the probability of A plus the probability of B minus the probability of the intersection. Okay. But the probability of the intersection is a non-negative number. So we're subtracting a non-negative number, we'll get a number which is less than or equal to the probability of A plus the probability of B. So we get the probability of A union B is this number here, which is smaller than or equal to the probability of A plus the probability of B. Right? Okay, so and this last result, even though it is simple, looks simple, and it is simple, and it is simple, probability of A union B is less than or equal to probability of A plus the probability of B is called the union bound, and it's actually very useful and used to prove very interesting results. Okay, so so this leads us to the 1.4 million question, and here it is. So I figure that now that we're all experts in probability, we should be able to solve this very easily and get this reward. So here's Linda. She's 31 years old. She is single, outspoken, very bright. She majored in philosophy, and as a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. Okay, so this is Linda right here. Okay, and the question we have about her is simple. Which of those is more probable? Which has the higher probability? Okay, simple probability question. 1, Linda is a bank teller. And 2, Linda is a bank teller and is active in the feminist movement, as you can see on the right. Okay, so which of those is more likely, that Linda is a bank teller or bank teller and active in the feminist movement? Okay, and maybe you can think about it. Pause if you want the video, think about it for a little bit, and once you have the answer, hopefully you can see a poll below, and if so, maybe make your selection. So here you don't see it behind my picture, but we ask whether she's bank teller and active in the feminist movement. All right, okay, so hopefully you've reached your conclusion, and so let's see the solution. So this question about Linda actually was part of a pretty well-known paper by Tversky and Kahneman. And they did this experiment. They asked 88 University of British Columbia students, and which is more likely, she's a bank teller or bank teller and activist in the feminist movement, and 85% of them, the vast majority, said she's more likely to be a bank teller and an activist. Okay, now let's see what happens. Let B stand for the event that Linda is a bank teller, and let A stand for the event that she's active in the feminist movement. Then what we're asking is about the probability of B, the probability that she's bank teller, versus the probability that of B intersection A, that she's a bank teller and active in the feminist movement. Now, if clearly B intersection A is a subset of B. So if you remember, the result that we said was so obvious that the probability of a subset is always less than or equal to the probability of the superset. Then, so B contains B intersection A. So therefore, the probability of B therefore must be bigger than or equal to the probability of B intersection A, contrary to what 85% of the students thought. Okay, so Tversky and Kahneman used this to suggest that maybe the way we think about probabilities is a little bit irrational. So that humans have irrational probability concept of probabilities. And actually studied not just this problem, they studied a whole bunch of problems. They call this phenomena, they call it the conjunction fallacy, and they showed other examples of conjunction fallacy. For example, they looked at Bjorn Borg. Just for those who don't know, he was the preeminent tennis player in the late 70s. He won, for example, 6 French Opens. He won Wimbledon for 5 consecutive years, 76 to 1980. All 5 of them he won it. So by the end, he was the best known tennis player by far at the time. And so they conducted this research in 1980, Tversky and Kahneman. And so just after he won the 5th one, and so they asked, suppose that Borg reaches the 1981, the next year's, following year, Wimbledon finals. Suppose that happens. Which one is more likely? Is it more likely that Borg will lose the first set, or that he will lose the first set but win the match? So again, you can see here that given where he was in 1980, it's very unlikely that he'll lose the first set, and it's also very likely that he will win the match. So perhaps not surprisingly, 72% said that it's more likely that he will lose the first set but will win the whole match. But again, we can see that B is a subset of A because B is lose the first set and something else. So it's a subset of A. So therefore, the probability of B must be less than or equal to the probability of A. So 72% for this question 2 got the answer incorrectly. Okay. Now, just in case you wonder what happened, 1981 rolled in, and Borg indeed reached the final. However, he won the first set. He did not lose the first set. He did win it, but he lost the match, and he lost it to John McEnroe. So just goes to show that maybe none of these things was actually as probable as the researchers thought. Okay? And then in case you're further curious what happened after that, well, 1983, just 2 years later or less, he actually retired at the age of 26. All right. So, but going back from Bjorn Borg to Tversky and Kahneman, they actually got the ultimate reward. So what they did was they looked at many probability perception studies. They studied a whole bunch of them, but of all of them, the Linda problem is the best known. And in 1996, unfortunately, Tversky passed away. And then in 2002, Kahneman won the Economics Nobel Prize. And the citation said for integrating insights from psychological research into economic science, especially regarding human judgment and decision-making under uncertainty. and here he is getting the Nobel Prize. And just in case you're curious, no, the award was not $64,000, but in fact the Nobel Prize comes with $1.4 million, although he did share it with another person. Okay, so I should be fair and to say that there's actually some criticism of the Linda problem. And there are different types of criticisms. Many of them I don't understand, but perhaps what seems to me like the most reasonable criticism is as follows: that when we ask multiple choice and ranking questions, then often the options that we give people are disjoint. For example, we ask people, do you want coffee or tea? Coffee and tea are two disjoint options. Or do you want your tea hot or cold? Two disjoint options. Or do you want to, even if you want to do ranking, like they asked here, they ask you to rank Monday, Tuesday, and Wednesday for the time for a meeting. These are disjoint options. That's what people usually give you, disjoint options. Even when the options are not explicitly disjoint, then we still interpret them as disjoint. For example, if someone asks if you want your coffee with milk or with milk and sugar, typically we'll interpret to be with milk only or milk and sugar, right? And if they ask you, do you want to meet Monday or Monday and Tuesday, then most people interpret to mean, do you want to meet Monday only or Monday and Tuesday? Okay, so if you do that, then it could be that the students had similar interpretation for the Linda question. So when they were asked if Linda is a teller or a teller and an activist, it's quite possible that they interpreted it as is Linda teller only, namely teller and not activist, or teller and activist. And if they did that, then the answer could be reasonable, because that means that they just said that Linda is more likely to be active in the movement than not active in the movement. So she's more likely to be teller and activist than teller and not activist. So maybe they were asking this question. Okay, but regardless of whether this question was correctly phrased or not, the bottom line is that humans are only moderately good at estimating probabilities, and there are many things that we don't do well. And so the problem is actually not just the $64,000 question. It's not even just a $1.4 million question. If you look at Madison Avenue or Wall Street, they make much more out of being able to evaluate probabilities better than humans do, and being able to see where humans don't judge probabilities exactly right and take advantage of it. Okay, so to summarize, we talked about probability inequalities. We again started with the three axioms. We talked about several inequalities. I should mention the union bound is quite important. We also said the probability of a set is bigger than or equal to the probability of its subset. But as we saw, sometimes we don't quite grasp it that way. Right? And what are we going to do next time? We'll discuss conditional probability. See you then.